everyone. So for this video lecture, we are going to talk about the hyperbolic functions, specifically those derivatives that we have in order to differentiate a specific equation. And I would like to introduce you first this sixth equation, wherein those six derivatives came from this definition of a hyperbolic function. So hyperbolic functions are functions that determine the right half of an equilateral hyperbola, just like trigonometric functions determine a circle. And mind you that this is not yet the rule for getting the derivative of a hyperbolic functions. I just only introduced to you or give you this six equations because from this six equation, it rooted to have the result of the sixth rule for derivative of a hyperbolic function. So our mathematicians use this definition of hyperbolic functions to get the six rules again for the derivative of hyperbolic functions. And yeah, I'm going to provide you those six already, and those six are this. So literally, we are going to use this rule for finding the derivative of a hyperbolic function. And notice that the first three are positive, the upper part, and the final three and the bottom part are negative. And besides, these derivatives are pretty much the same as the derivatives of a trigonometric functions. But unlike in the trigonometric function, we have negative sign there when you're getting the derivative of a cosine. But here in a hyperbolic function, we have positive sign. And as well as on this part, on the trigonometric function, when we are getting the derivative, we have a positive secant x tangent x. But in this part, we have negative as our sign right now for the rule. Okay, so we're done. I hope you take down of this or take note of this six rule for finding the derivative of a trigonometric function. Again, those first are the previous slide that I provided to you or that I showed to you. That is not yet the derivative of hyperbolic function. So these are the rules itself. And we're going to use this to apply in our example. So first up, we are tasked to get the derivative of a hyperbolic cosine squared x over 2. And we're going to use our chain rule. So you'll already know that the format for using the chain rule will be n, which is our value for the exponent times u raised to n minus 1 du. And again, our n is the value of the exponent, and then u raised to the n minus 1. So when we have as much a function that is raised to any number, any value of exponent, when we are getting the derivative of that, you will be needing to always deduct or subtract 1 and then times du. Du represents the derivative of the function itself inside the parentheses. Okay, so in this part, our u will be the hyperbolic cosine x over 2. And after this, we're going to temporarily stop on this part because we're going to get the du, or the du value itself, for us to be able to apply in this part, which is our rule for getting the hyperbolic cosine function. So we have hyperbolic sine u du. This is our rule for this given. And our u here is x over 2, and the derivative for x over 2 is 1/2. And yeah, just focus in this part right now, and then plugging in these values, the one that we already found out. So we're gonna have this kind of equation for our du. Will be hyperbolic sine. Our u is x over 2 times du, which is 1/2. And since we have 1/2 here at the end part, we can be able to move it on the first part before the hyperbolic sign. And we're gonna have this kind of equation, which is 1/2 hyperbolic sine x over 2. Since we have the value of du already, we're gonna use this value of du in our format for the chain rule. And again, since we have our exponent here, which is 2, so it will become our constant 2. Okay, it will become our constant 2, and we're going to put it at the beginning of our equation. And then write down the u as well. And then our exponent 2, we're going to deduct 1 from it. So our exponent will become only 1. And yeah, so our equation will become 2. Our u is cosine x over 2 times our du is 1/2 hyperbolic sine x over 2. I'm sorry, I read this at cosine x over 2, but this can be read as hyperbolic cosine x over 2. Okay, let me just remove this reds. Right, so since we have this kind of equation right now, we can be able to remove this and cancel this. Since we have 1/2 on this part, and then the numerator 2 on this part. So the remaining terms that we have will be the final answer for getting the derivative of a hyperbolic cosine squared x over 2 is hyperbolic cosine x over 2 hyperbolic sine x over 2. Alright, so let us now move forward for getting the derivative of a hyperbolic cosecant 1 minus 3x. We're just going to use this rule for finding the derivative of hyperbolic cosecant function. So we have negative hyperbolic cosecant u hyperbolic cotangent u du. And first we're going to get the u itself. Our value for u is 1 minus 3x. And yeah, we're going to get the du as well. So again, du represents our derivative for the u itself. Since we have constant 1, so automatically we have 0 as our derivative. And for derivative of negative 3x, we're gonna have negative 3. So we have the value already for u and du, and just going to focus in this rule. Plug in this value, and we're gonna get negative hyperbolic cosecant our u 1 minus 3x. Hyperbolic cotangent our u 1 minus 3x times du negative 3. And since we have negative on this part and this, we can be also multiply those two so that we can get a positive 1. And then after that, we can be able to move this 3 to the first part of our equation, and we're gonna have this. So the derivative for the hyperbolic cosecant 1 minus 3x is 3 hyperbolic cosecant 1 minus 3x hyperbolic cotangent 1 minus 3x. This will be our final answer. Okay, so let us move forward right now. The next example that we have, say we are tasked to get the derivative of hyperbolic tangent e raised to the x power. So again, go back to our rule, and the rule for getting the derivative of hyperbolic tangent is hyperbolic secant squared u du. And of course, first task is to get the u and the du value. So our u is e raised to the x, and since we have the base which is e, so it will be the same for the derivative of e raised to x. The derivative will be e raised to x as well. And we have the value of this two already. Focus on this rule, plug in this value, and we're gonna get this. Hyperbolic secant squared e raised to the x times e raised to the x. And after we did that, we can also move this e raised to the x on the first part of our equation. So the final answer, or the answer for getting the derivative of hyperbolic tangent e raised to the x is e raised to the x hyperbolic secant squared e raised to the x. And let us now take a look on how we can be able to apply the derivative for finding this hyperbolic secant to the 4th power 10x. And again, we're going to use the chain rule on this part. Chain rule basic format will be n u raised to n minus 1 du. And again, our n is automatically the exponent itself, which is 4. And our u is our secant or hyperbolic secant 10x. And we're gonna stop temporarily on this part because we are going to get the du value. So how to get that? Focus in this. This is the rule for getting the derivative of a hyperbolic secant. So that is negative hyperbolic secant u hyperbolic tangent u du. And our u is 10x. So what is the derivative for 10x? The derivative for 10x is 10. So this will be our value for du. Since we have u and du already, so again, focus in this part of our rule, plug in this value, and we're gonna get this. du is equals to negative hyperbolic secant 10x times hyperbolic tangent 10x. And we have the constant here as well already on the last part, and we can be able to move it in this part. So we have this negative 10 hyperbolic secant 10x hyperbolic tangent 10x. So we have the value of du already. So we found out the du already right now, and so you just continue this chain rule process. Since our exponent is 4, so we're just going to use that as our constant and move it or write it down at the first part of our equation, and then write down what is the u, and then our exponent, which is 4, subtract 1 from it. So we're gonna get our exponent, which is 3, right? Or it will be raised to the power of 3 only. And now after we did apply that, we can be able to have this kind of equation, which is 4 our n, and then times u. Our u is hyperbolic secant 10x raised to 3. Why it is raised to 3? Because we have this n minus 1. That's why it's been raised to the third power. And then multiply to our value of the u, which is negative 10 hyperbolic secant 10x hyperbolic tangent 10x. And as you can see in this part, we have two constants here that we can multiply together. So we have negative 10 times 4, we're gonna get negative 40. And after that, we have 3 hyperbolic secant 10x here. And we also have another one hyperbolic secant 10x. So we can add this and then we can add this and then we're gonna get the hyperbolic secant 10 raised to the 4th power. So meaning our equation will become, for getting the derivative of the hyperbolic secant to the 4th power 10x, our final answer will become negative 40. From negative 10 times 4, we have negative 40. So we sum up the hyperbolic secant 10x cube plus the hyperbolic secant 10x. That's why we have hyperbolic secant to the 4th power 10x, then times the hyperbolic tangent 10x. Alright, so let us move forward right now to our last example. So we're going to find the derivative of a natural logarithm hyperbolic cotangent 7x. And as you remember from our previous topic, for the rule for finding the derivative of a natural logarithm will be 1 over u times du over dx. Or to simplify it is like du over u. Alright, so for the derivative of our natural logarithm, simply du over u. And first up, we're gonna get our u is automatically the function itself inside the parenthesis, which is the hyperbolic cotangent 7x. And then let us stop here temporarily again and use this rule for finding the derivative of a hyperbolic cotangent. And the derivative for hyperbolic cotangent rule is negative hyperbolic cosecant squared u du. And our u in this one is 7x, and the derivative for 7x is 7. So that is our du. So we're gonna focus in this part again. We have the value of u and du, plugging in these values, and we're gonna get this. Negative hyperbolic cosecant squared 7x, our u, and then times du, which is 7. And then again, we have this constant at the last part, so we can be able to move it at the beginning of our function. So we're gonna get this. Negative 7 hyperbolic cosecant squared 7x. And after this, we're gonna start to apply the derivative of our natural logarithm. So we're gonna use the du over u. And again, the value for du is this, and our u is this. Just plug it in. So we're gonna get negative 7 hyperbolic cosecant squared 7x over hyperbolic cotangent 7x. And this 2 hyperbolic cosecant 7x, we can spread it out like this. We have negative 7 hyperbolic cosecant 7x and another hyperbolic cosecant 7x. We have x here. Alright. And then, yeah, we have the final answer already. So I'm just going to explain to you why we got this kind of final answer. Since I spread it out, the hyperbolic cosecant squared 7x, as you can see, this, we have identity here. The identity for our cosecant and cotangent is secant. Again, the identity for our hyperbolic cosecant and hyperbolic cotangent is hyperbolic secant. Okay? And yeah, so just put in what will be the remaining values, and we're gonna have this final answer, which is the negative 7 hyperbolic secant 7x came from this times hyperbolic cosecant 7x, which is this. Alright, and again, our final answer for getting the derivative of the natural logarithm hyperbolic cotangent 7x is negative 7 hyperbolic secant 7x times hyperbolic cosecant 7x. And that will be all for our hyperbolic function. Thank you so much. God bless you.